Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. If you're joining us live, please make sure that you type in your questions anytime throughout the webinar. You don't have to wait until the presentation is over. We'll happily queue those up in the chat window to ask on your behalf when it is time. And if you let us know where you're joining from, what grade your students are, anything like that, we would be happy to give you a shout out when we ask your question. So today's guest is Dr. Sushanta Mitra. He is the Executive Director and a Professor at the University of Waterloo Institute for Nanotechnology. Thank you so much for joining us, Dr. Mitra. I will let you take it away.
Oh, good afternoon. Thank you so much for having me here. I'm so excited to talk about some of the really interesting things that my research group has done over the years, which has a significance in terms of solving some of the global challenges that we see today. So if you look at the global challenges of today, these are some energy, water, food, environment, public health, and often these come through community engagement process where communities are telling us these are some big challenges, global challenges, and how we as a research community are able to address this. So I'll take a few examples as in the next 15 minutes to tell you how we have addressed some of these. So the first is the water is very important. It's a precious commodity. Luckily in Canada, we have one of the largest freshwater reserves in the world, but there are places where there is a huge shortage of water as well. And if you look at North America itself, this figure shows that there's a lot of boiling advisory happening in places like in US, more than 500 to 1,000 boiling advisories. And we in Canada are also not immune to this because we can see that sometime in Walkerton in 2000 we had a big challenge in terms of E.coli contamination in water. So my group tried to see how we can detect E.coli in water, because if E.coli is present in water, that means that water is contaminated. There could be possibility of other viruses, norovirus, giardia, and other waterborne diseases. So it's a good water quality indicator. So we apply chemistry. So what happens is E.coli cells has particular enzymes they secrete, which is beta-galactosidase and beta-gluconeidase. We bring a molecule, like these are chemical molecule, which kind of attack these enzymes. So for example, red gull is a molecule which can attack beta-galactosidase, or a mug is a molecule that can attack beta-gluconeidase. The way it works is that when I have an E. coli present, so as I mentioned, the E. coli will give out the enzyme, which is the particular enzyme, beta-galactosidase, so that this molecule gets cleaved, and then you get indigo color. Okay, and this indigo color is visible to you in a naked eye, so you can see the red color happening and so forth. Similarly, another is a process also. Another molecule can be cleaved, and you can get something which we call it as a fluorogenic compound. Means that if I shine a laser source with a particular wavelength, it will emit a different wavelength, which can again be detected. So what we did is we created a cocktail of various compounds here. As you can see, that we put some mug, we put some lysing agent so that the enzyme can be secreted and so forth. And we see that if there is no E. coli versus there is an E. coli present, you can see there is quite a significant increase in the intensity of the red color. So these are done in a chemistry lab, in a test tube, and these are called centrifuge tube. But we said let's make a device out of it so that you can yourself can do a testing of water. So that's what we did here is we created a mobile water kit where you can take 100 ml of water. There is a filter where you push the water through it, and then you add these chemical compounds A, B, C, D in a sequential order on top of this filter, and you see if there is a color change, then there is an E. coli present. If there is not, there is no color change, no E. coli present. Often we found through our exercises that these regions of the world often will not have access to clean drinking water, but they will have access to cell phone. So I said, let's use the power of cellular network to do something more. So we partner with software developer. We developed an app where we take, go to different wells, take the image, send it to the server, and we have a priori taken all the cell phone numbers of all the users of the given well. For example, if this well is contaminated, it's sending a text message saying that well 3 is a positive for E. coli. So it becomes a very useful tool for water quality monitoring through using an app-based cell phone as well. Bear in mind, cell phone you don't need as such, because anyway you can see the water quality, whether the water is E. coli or not, right using your on the color of the filter surface. But the app gives additional functionality so that it can give you an early warning system as well. So the reason why we are able to do this is because we are able to create a very strong, test bed in terms of looking at having our public health centers, having our hospitals, having NGOs together to deploy these solutions. These are some of the pictures that we're doing field tests, taking samples of water, collecting and doing field tests and so forth. So what we have done is that we have taken everything from the lab and all the way we went to getting into the field. Let me play a video which will give you an idea how this could be, how we have achieved this in a field scale. Just bear with me a second. So I'm playing a video.
It's a new technology that promises to make drinking water safer for hundreds of millions around the world. Sushanta Mitra, a professor of mechanical engineering at the University of Alberta, has developed a system for quickly detecting E. coli bacteria in water sources, instantly spreading the word to vast numbers of people through cell phone networks.
From any water source, be it well, tap water, we take 100 ml of water, put it into our M-Water kit. If there is an E. coli, it will do a color change on that kit on the sensor surface, and that sensor surface we take an image with our cell phone, which has an app running, E. coli app, and then that images get transmitted to a server which will tell to the end user that there is an E. coli outbreak, if there is, and if there's not, it is safe to drink the water and so on. Typically, a traditional system will take 24 to 48 hours, but our technology, based on the level of contamination, anywhere between 2 minutes to 20 minutes we can detect.
Mitra and his team have successfully completed 2 field trials in small, impoverished communities just outside the city of Mumbai in India. The next step is to test it inside India's most populous city, where it could impact millions.
In April, we are going into a municipality in Mumbai where it is millions of people are accessing the water, and we want to show that this technology is equally applicable to not only to the small communities, but as a scale-up operation for municipalities as well. We're talking about close to 400-500 millions of people in these kind of large countries like India, China, and so on.
Through a U of A-sponsored initiative called Engage North, Mitra is now also introducing his E. coli detection system to Canada's northern communities, where clean, safe water is often as hard to come by as in developing countries like India.
We are trying to connect our undergraduate students, our graduate students with the communities in the north. So last summer we have a lot of interaction with the community in Penticton and Nunavut. And right now we are working with 2 more communities, Dene communities. It has a huge amount of impact in terms of public health. Access to clean and safe drinking water is a global problem. And what we are doing, we are empowering those bottom billion people, telling that they can individually decide what water is safe for them.
So let me move back to the presentation, and so that shows, these kind of uh, things can be very powerful tool in terms of deploying solutions for the masses. Also, what we do is we have um, uh, we took this things what we learned from that deployment, and we made it available through another way, which is much easier, where you don't need to dispense everything. What we created is a very simple plunger tube system. At the bottom of the plunger, we keep a porous material, like a spongy material, where we put all the chemicals in, and then you push it, and then again the same thing happens. In the next slide, it shows it's a very simple, what we call it, a do-it-yourself test kit. So anyone in your school, you can try this. You pour water in this tube, push the plunger in, and if there is an E. coli present, the color changes happen. So it's a very simple technology. We also do things on a chip level, make it a very small, tiny chip. So you can see that these are 100 micron wells that we have created. So 100 micron is typically a thickness of your hair. So that small things we can make as well. And also we use another way is like, people who has a lot access to glucometer. So we tweak it such that we add some glucose molecules, so that at a delactose molecule, so that at the end you get as a glucose as a product. So that becomes again a way to use existing glucometer to deal with E. coli detection. Say for example, this is what the technology talks about, is that you dip a glucometer, a paper strip is there in the glucometer, you add some delactose molecule into a glass of water that you collect from your faucet, and then see if that there is an E. coli present or not. We also did further what we refer to as a frugal innovations. Can we have a technology which is almost like cost you cents? So what we did is we take a paper, so simple paper that we use every day. So we kind of lysed that paper at the front end with some glucose. So it's like a sugar molecules. We add some sugar. At the very end, we put some our enzymes, our chemical compounds, and so forth. And what we do is that, again, if there is an E. coli, you can see the color change will happen right at that location. The principle is very simple, is you take a glass of water, what we call it is a dip test. So you dip that thing, this dip test, the solution, the paper strip, because there's a sugar molecule. So if there's an E. coli present, they will try to get attract to that sugar molecule. So it's like a fishing of E. coli, if you will. And then this E. coli goes inside, because paper is a porous material. Water will weak with it. So the E. coli will weak with it, and then it will go into the reaction area, and you can see the color change. So it becomes a very, what I call a low cost technology for the masses. So I guess in a 15 minutes time, I can give an overview of how we have talk about a technology where there was a real challenge from the community. The question came from the community, whether in terms of having a technology that will allow them to have a rapid detection of water quality, and through a series of innovative steps, right from mobile water kit 1.0 to mobile water kit 2.0, and now and this dip test, almost like a few cents it costs. I can show you the landscape of a technology that can meet community need. Thank you so much, and I'd love to take any questions and comments.
Thank you very much. I'll just direct you to click on the red stop share button now that we've finished the slideshow. It should be near the top of your screen, and you might need to hover to get that in view, and then we will be able to see you a little bit larger on the screen while you answer questions. So have you found that red stop share button at the top there? I
Yeah,
still see
yeah.
yours. There it is. Okay, perfect. So my head is still kind of exploding right now with the idea that you were able to take a device that is commonly available for people who suffer from diabetes and need to monitor their blood sugar, and you have adapted that to detect a level of bacteria. And the idea that I'm wondering is, can you quantify to some extent or get some relative reading on that meter to say how much bacteria is
Yeah,
in that solution?
yeah. So the typically a blood glucose meter, the same glucometer, it works on the level of glucose in the blood sample through a electrochemical reaction mechanism in this system. The same thing what we are doing is end product, we are getting glucose. So amount of E. coli is correlated with the amount of glucose present in the output of the system, and the reading that the glucometer shows actually shows how much E. coli present in that.
Wow. Okay. Yep. For everyone watching, my mind is blown a little bit right now. Just that idea, that innovation, you're taking something that already exists and is readily available and making it work for a completely new investigation. So maybe the next question I have for you while our students are getting their questions together is, did you go ahead and do the testing in Mumbai? The video mentioned that
Yeah,
that was the next step.
yeah. So I should mention that video, as you have seen, this is done when I was at University of Alberta. So this is almost like 2013. And so we have gone along. So we are talking about 2018 now. So 5 years now. I have my own startup, a Glacier Clean Technologies Incorporation. Not only in India, so we do in US, in Los Angeles County. We do it in Europe, in UK, and also in Australia and New Zealand. So we are pretty much everywhere we do field trials now.
And so you started with a pure sort of theoretical research, then into sort of applied research. You said you've taken this, commercialized it. You have a startup company that's producing these water test kits and that sort of thing, and they're being used. What is that process like? We talk a lot about entrepreneurship for our students, but maybe you can give us a
Yeah,
view into what that's been like for you.
yeah, because I felt that as a researcher, we write a lot of peer review publications and so on. So which has my research group draws, and that's has an impact. But I felt that I need to do something which has a important social impact and really solving some of the global challenges. And we felt we have the expertise to do that. We have to just get around, go put our minds together, go into the drawing board, and see how we can create a paradigm shift in the technology and come up with a different angle to it. So I believe the reason this entire journey could be possible, because if you want to sum up in one sentence, because I came out of my comfort zone. I'm a mechanical engineer, and I didn't know anything about biology, nothing about chemistry and so forth. So I thought this is a challenge I should take. I learned my group, I put together the people and so forth, and really came out of my comfort zone to tackle one of the critical problem in water quality monitoring is the rapid detection of pathogens in water.
Right. And so that brings me very nicely to my next question here of, who do you collaborate with? It sounds like there's a team. Like it's
Right.
not just Dr. Mitra who's putting out all of these things with only what's in your own head. Who do you
Yes.
collaborate with on projects like this?
So what we do is we have to have when we first develop things in our labs in terms of testing and so forth, where I have my graduate students, my postdoctoral students, and then research associates. So that's an internal team. But often researchers leave up to that. That provides publications, peer review publication, but we went an extra mile in terms of what I call as a translational research. We moved the lab research into the field. In order to do that is you have to create a team in the field. So I have my team, which is the public health agencies who run the hospitals, because these are the people who have the community people who know about the problem, who have the access to the field. Then similarly, we'll have the NGOs who will actually go house to house to collect the water sample, do the testing. So you need really a team effort in order to deploy the technology.
Right. So I understand that you are at the Nanotechnology Institute there at Waterloo. Are there other projects that you work on as well as these water quality projects?
Yes, so we have other in terms of detecting others like foodborne disease bacteria like Listeria mono and so forth. Then other sensing, detecting biomarkers. So there are wide applications of various micro nanoscale science and technology that my group does.
Very nice.
And also in energy area. So we work in green energy in terms of fuel cells, understanding how fuel cell works, and environment. For example, how if you have an environment, but today due to time constraint, I can share with you all, like if there is an oil spill, so we have developed technologies how you can rapidly remove oil from these kind of oil spills, and so you can protect the marine ecosystem.
Right. That seems like quite the widespread of different projects that you're working on. That's really amazing. I'm just writing out our next question here so I could relay to you from Ms. Gummer's class. They're grade 4s at Hillcrest in Campbellford. And they're wondering how and why you took the career path that you took.
So I think the critical when I reflect myself, I always have been curious. I was curious about the things that happens in nature, and I found engineering pathways one way to answer those curiosity, and I see what is happening in nature, and I'm trying to provide a physical understanding of the processes that we see, starting from how raindrops wet a surface to things that we see in terms of understanding nature is water, is ecosystem, and so forth. So I believe that is the and a career path I took. And of course you have to love science and maths. I was fortunate that I got a significant mentor, and I think that's so critical. When I look back, I think those teachers are the ones who actually helped me to where I am today, because they provided that knowledge, that pathway, so that I can think big, I can question things, and I can meaningfully answer those questions.
Right. And next we have a question from Mrs. Martello's class in Brantford. And they were wondering how you came up with the idea for the mobile water kit, maybe version 1 and 2.
Yeah, so I think that's where my background of mechanical engineering also come into play, because we understand designs, we understand ergonomics, how human individuals will able to use a technology. So we create an embodiment, and that's I see is the mechanical engineering design, so to speak. So that helped me a lot in my background in engineering.
And just to go over, you briefly mentioned, but Mrs. Martello's class was also wondering what motivated you to tackle the water quality issue in particular.
Yeah, because what we see globally, if you look at the WHO, World Health Organization, they say that 70 to 80% of diseases globally is due to waterborne disease. So we felt that if you are able to target this, this is fantastic. And the reason I targeted this, because it's not that I was looking for the problem. The problem came from the public health center in the remote village in India, where they were bogged by waterborne diseases, and so they were not able to take care of really the key challenges like tuberculosis and other life-threatening diseases. So they thought if there is a way water quality could be monitored, so then quickly they can provide water boiling advisory, so that it is less stress for public health. And that's how it kind of motivated us to look at this problem.
Right. And you mentioned a little bit of work in the oceans, which made the grade 4s at Hillcrest wonder if you'd ever considered tackling a project that tries to get the microplastics out of the ocean. It's very hot topic now.
Yeah, it's a very good questions. And plastics, as you imagine, is created, but it is now creating a huge environmental challenge. So I think there is a big research and directions going on in terms of biodegradable plastics and so forth. So hopefully that will come into existence and available commercially, so that we don't need to worry too of the kind of human generated pollutions that we have created. It's a tough problem to tackle, because decomposing plastics is very challenging.
And back to the mobile water kits, you talked a bit about the app that was designed to go along with them, and it seems that the app doesn't help in particular with the testing, but rather with getting the word out.
Yes,
right.
yes.
So who did you end up collaborating with, or how did that happen for developing an app? Because that's obviously not what you might have as a personal expertise when you're already an expertise in engineering and you're learning the biology and the chemistry. How did that happen?
So I knew that this is cell phone is a powerful technology because it's available to everyone, and if you can harness the technology, that means you are able to reach to a huge population. So I hired some high school kids who are app developer, and then they worked with us, and then we are able to develop this app along with the software vendor who will really provide a finished product.
So involved in your team, they were actually high school students.
Yes.
Wow.
So every summer I take a lot of high school students, because I think that they're two-way things. So I believe these are the new generations who are bringing different kind of skill set to our group, and at the same time the young minds can see what research is about, what post-secondary universities are about. So there is a two-way flow of knowledge in this case, and that really excites us.
Wow. Well, there you go. To the students who are watching, I believe our classrooms today are not that far from you. So something to inquire about lately if you're passionate about what we're talking about today. I guess I'd like to finish up today. We've only got a couple minutes left. I'd like to ask if you have any advice for students who are listening today and might want to become engineers or entrepreneurs. What would you tell them?
I think the couple of things I can mention is be curious, and always listen to your teacher. They are the best.
It's very simple today. Stay curious and listen to your teachers. Excellent. Well, thank you so much for joining us today, Dr. Mitra. We really appreciate your time.
It was really a pleasure. I'm glad that I got this opportunity to interact with everyone in the school. Thank you.
And just to let everyone know, next week on PIR Live event, we are celebrating Science Odyssey, continuing to celebrate Science Odyssey with webinars about water quality and forensic science. So if you're into the water quality topic, then you can join us again next week for a couple different aspects about that as well. And other webinars, information available on our website at pirweb.org. Thank you so much for tuning in today, and I hope you enjoy your weekend. Goodbye, everybody.